Good morning one and all. My name is Dr. D.V. Manjunatha. I am working as a senior professor in the Department of Electronics and Communication Engineering, Alvas Institute of Engineering and Technology, Modbidri. Now I am my topic of presentation will be module 2 of basic electronics, which is BJT biasing and operational amplifiers. Today I will be starting with BJT biasing, which is session 1. So before going to study the BJT biasing, we must know the prerequisites of BJT biasing. So as we know that BJT is a three terminal 2 PN junction device, a semiconducting device. It has 3 terminals. They are emitter, base and then collector. Let us take the symbol, all those things on the board. So the BJT symbol is like this. So this is a base, emitter and then collector. If we want to see the junctions between the different 2 junctions of BJT, we need to go for the structure of BJT, which will be like this. This is emitter, then base and then collector. This is let us say NPN transistor. Of course, this is a NPN transistor. In an NPN transistor, this PN junction is called as, we call it as base emitter junction or emitter base junction, which we call it as JEB. And then here one more junction is there, this PN junction. This PN junction we call it as JCB, collector base junction. Like this we can define the BJT. We can consider the BJT as 3 terminal device and it has 2 PN junctions. They are JEB, the emitter base junction. Next is the collector base junction, JCB. Now, before going to transistor biasing, we need to study 3 regions of operations of BJT. The 3 regions are, one is cutoff region, second one the saturation region, third one is the active region. Why we have to study these 3 regions of operation? Because we must know where exactly we have to operate the transistor in the particular applications. So when we take the applications of BJT, there are so many applications, out of which major applications are, first one is amplifier application, second one is oscillators, next is transistor can be used as a switch applications. These are the major applications which we use in electronics by using BJTs. So when we consider biasing, we will be considering most of the time the amplifiers. Why amplifiers is because when we consider oscillators, oscillator is a circuit which consists of amplifier and the feedback network. So here also BJT can be used as an amplifier. So amplifier applications plays a very important role with respect to BJT. So 70 to 80% of the BJT applications are amplifiers itself. Therefore, we will be considering amplifier as an application when we discuss the transistor biasing. Now, what is switch? Switch can be the BJT can be used as an electronic switch. So how exactly we can use BJT as an electronic switch? So in electronic switch application, we will be operating the transistor between the cutoff region and the saturation region. And when we consider amplifier, we will be considering the amplifier in the active region of operation. So coming to amplifier application, what is the application of an amplifier? Application of an amplifier is, let us say, in a common this thing, in the society, very best example of amplifier is that in a cable TV application, cable TV applications. Let us say the cable is not coming properly, we will be calling the cable operator and we will be complaining about the cable, the channels are not coming properly, lot of distortions are there, we will tell. At that time, you will check and install all the cable this thing, then he will then also the problem is not rectified, then he will say immediately, sir, tomorrow we will come and install the amplifier nearby our house. So, the best example for amplifier is cable TV. So, next day he will install the amplifier and the channels will be coming properly. That means amplifier strengthens the weak signals, thereby the cable channels are coming properly. The best example of amplifier. The next example of amplifier is we can use the amplifiers in stereo systems to increase the audio, etc. Now, when we take the amplifier, the BJT in the amplifier must be operated in the active region. Let us now touch on the different regions of operations of BJT. One, the active cutoff region. In the cutoff region, as we discussed, there are two junctions. One is JEB, JCB, emitter based junction, collector based junction. Both these junctions must be biased in such a way they are reverse biased. Both the junctions in cutoff region are reverse biased. In saturation region, both the junctions are forward biased, and in active region, emitter based junction is forward biased and collector based junction is reverse biased. We will be using this application, this active region in active region of a BJT in biasing, because most of the applications of BJT lies in amplifiers. Therefore, while biasing the device, we will be concentrating on active region of operation. Even if we take the oscillator example, even in the oscillator also we will be using BJT as an amplifier. Therefore, amplifier application plays a very important role. Taking that into consideration, we will be considering the biasing. So, this is one of the important prerequisite for biasing. Next, coming to which configuration must be used in the BJT biasing or the amplifiers. So, when we in the first module we have already discussed, there are three configurations of operations of BJT. They are common emitter configuration, common base configuration and common collector configuration. So, when we compare all these three regions configurations, we have come across that common emitter configuration is the best configuration for the amplifier applications. Therefore, we will be using common emitter configuration in the BJT amplifiers. So, these are all the prerequisites which we have to consider, and one more prerequisite for BJT biasing is that we will be using the Kirchhoff's voltage laws and Kirchhoff's current laws. These laws plays a very important role. Last semester you might have studied basic electrical engineering. In basic electrical engineering, in all the circuits you have applied KVL, Kirchhoff's voltage law, Kirchhoff's current law. So, so these two laws are most important in the BJT biasing. So, KVL, KCL and to certain extent Ohm's law is used, right. So, one more important prerequisite here is the emitter base junction. If you see the area of emitter is moderate area. BJT base region is very thin region and the collector area is more. Why this is? Because when we go to emitter, the function of emitter is it acts as a source of charge carriers. It introduces, it gives this charge carriers, and then base, when we consider, the base controls the flow of charge carriers from emitter to collector. Therefore, most of the charge carriers we will be collecting in the collector region. Therefore, it has to dissipate lot of power. Therefore, the area of the collector region should be more, and since the function of base is to control the charge carriers flow from emitter to base. Therefore, the region of base is very thin, area of emitter is moderate, and the area of collector should be very large compared to all the three regions. So, these are the prerequisites of BJT biasing. So, most of the time we will consider the amplifier application. In amplifier application, we will be considering the active region of operation in amplifiers. So, we will be more concentrating only on the active region. Active region means emitter based junction of the BJT is forward biased, collector based junction of BJT is reverse biased. So, coming to this PPTs, let us consider BJT is a 3 terminal, as I already discussed. BJT is a 3 terminal 2 PN junction, 2 PN junction. It's okay. BJT is a 3 terminal 2 PN junction semiconducting device. The 3 terminals of emitter, the terminals of the BJT are emitter, base and then collector. The 2 PN junctions are emitter based junction and collector based junction. Now, for getting faithful amplification, what do you mean by faithful amplification? Let us discuss what is faithful amplification. Suppose we will consider this as an amplifier. This is an amplifier. This is the input and this is the output. When we consider the input, we will be applying the weak signal which is to be amplified or strengthened at the input side. This is the input signal, let us say Vi. And V out, we will note down at this point. The V out should be this one, amplified signal, but the frequency will not be altered. The frequency will not be altered. This is a time, this is V out. So, we say the amplification has taken place faithfully. We say the amplification is taken place faithfully means, faithful amplification means we have to get the amplified signal, both positive half and negative half should be equal. Then only we say it is faithful amplification. Faithful amplification has taken place. Therefore, what is faithful amplification? When we give a weak signal which is to be strengthened, it should amplify both positive direction and negative direction equally. And on the other hand, if we get the signals like this, it is not faithfully amplified. It is not faithfully amplified. Similarly, one more way we get is positive half will be more and negative half will be less. Then also the faithful amplification has not taken place. So, the unfaithful amplification has taken place. So, what is faithful amplification? Faithful amplification means when we give the weak signal at the input of the amplifier, we get the amplified signal in such a way the positive half of the amplified signal and the negative half of the amplified signal should be same amplitude should be there. Then we say that faithful amplification has been taken place. So, that is about the faithful amplification. So, for getting the faithful amplification, we the BJT must be operated in the active region. Then the emitter based junction must be forward biased and collector based junction must be reverse biased. Then we say that BJT is operated in the active region. Then the process of making BJT to operate in the center of the active region, by using a single battery is called as biasing. It is a layman answer. Let us go with the what is the actual answer, we will see the later. The learning outcomes of this session will be what is biasing. So, your syllabus starts with what is biasing, DC load line concept, and then bias point, problems on biasing and biasing techniques. To certain extent we will study the fixed bias technique. So, what is biasing? I will repeat, what is biasing? So, when you come to the class in the morning, 8:30 college is there, let us say. So, you are all staying in hostel or your house, whatever it is. Suppose if you want to come and sit in the class, you should have some strength in you. So, how do you get that strength? You will get that strength by taking breakfast. You will get the breakfast, and after having breakfast, you will come and sit in the class. So, you should have the food to come and sit in the class, then only you will get a strength and you will sit in the class. But how do you strengthen the devices, electronic devices? By providing DC voltages and currents. So, by providing DC voltages and currents to the BJT, we call it as biasing. So, giving DC voltage and current to the BJT to make it active is called as biasing. So, you are biasing. How do you bias? You will be biased by taking a breakfast or lunch in the afternoon, then you will be biased, then you will be very active and you can sit in the class. Just like that, giving DC voltage and current to the BJT is called as biasing. So, what is the food for the electronic devices? The food for electronic devices will be the DC voltages and currents. So, as we eat the food, just like that, we need to provide the food for the devices to make it active. So, one such definition of BJT biasing will be giving DC voltages and currents to the device is nothing but biasing. So, it is a layman answer. So, when we are all technical people, we must know what is technical definition of BJT biasing. So, what is definition? So, let us discuss definition. The proper flow of zero signal collector current, the proper flow of zero signal collector current. The moment I say zero signal, what is this? So, it is DC. Zero signal means it is DC. So, the proper flow of zero signal collector current and proper maintenance of collector to emitter voltage VCE during the passage of the signal is called as BJT biasing. When we in the exam, when they ask what is transistor biasing, giving voltages and currents to the device, you should not write that answer. Of course, to certain extent that answer is correct, but the proper definition will be the proper flow of zero signal collector current IC and proper maintenance of collector to emitter voltage during the passage of the signal is called as biasing. Now, why we are concentrated only on IC and VCE? When we take the BJT in CE configuration, what is the output voltage and what is the output current? The output voltage of BJT CE configuration will be VCE and output current of BJT CE configuration will be IC. Because we consider BJT CE configuration in the amplifier applications, in the biasing also we must consider the output configuration and the CE configuration of the BJT. The output voltage and output currents are VCE and IC. Therefore, we must properly maintain IC and VCE before applying the weak signal which is to be strengthened in the amplifier application. So, therefore, the perfect definition or the proper definition will be proper maintenance of zero signal collector current and proper maintenance of collector to emitter voltage during the passage of the weak signal which is to be amplified is called as biasing. Let us move to next slide. So, BJT biasing. Now, how do we make the biasing? So, as I told you, the BJT must be operated in the active region. To do so, emitter base junction must be forward biased and collector base junction must be reverse biased. So, by using a single battery, we do this active region of operation. So, in order to do that, we need to take the help of DC load line. So, what is this DC load line? What is the use of DC load line and what is its importance? I repeat the question, what is the use of DC load line and what is its importance? So, the DC load line is used to determine the operating point or the Q point or the bias point. This is a new topic, it is operating point or the Q point or bias point. So, what is this bias point? We will discuss that later. First let us discuss the DC load line. So, DC load line is used to determine the operating point or Q point or bias point of the transistor. It is helpful in fixing the operating point at the center of the active region. So, as I told you, we need to operate the BJT in the active region, not that is not sufficient. We need to operate the BJT at the center of the active region. How do we do that? We do that by using the DC load line. For what we have to operate this BJT at the center of the active region for getting the faithful amplification. So, the DC load line is used, okay, next let us move to next PPT, next slide. The DC load line, what is DC load line? How to draw the DC load line? What is DC load line and how to draw the DC load line? The DC load line is a straight line drawn on the characteristics, output characteristics of BJT, which intersects the saturation point and the cutoff point respectively, right. So, before going to DC load line, we need to know what are the output characteristics of BJT, under CE configuration. Let us draw the output characteristics on the board. So, the output characteristics looks like this. So, as I told you, IC, what is output characteristics? Output characteristics of BJT in CE configuration, it is the graph of IC versus VCE keeping the base current or the input current constant. So, let us draw the characteristics. It is VCE here, x axis is VCE, y axis is IC. So, this is one characteristics when IB equal to 0. When we maintain IB equal to 0, when we apply VCE and increase the current, we get this characteristics. So, these are the output characteristics. So, let me call this as IB1. Let me call this as IB2, IB3, IB4. So, in this region below IB equal to 0, the region is called as cutoff region. So, this is a cutoff region we have already discussed. Okay, colors. Cutoff region. Then the region this side is called as the saturation region. And this region between the saturation and the cutoff is called as the active region, this region. We have already discussed what is cutoff region. In this region, emitter base junction is forward bias, emitter base junction and collector base junction both are reverse biased, and saturation region is a region wherein emitter base junction and the collector base junction both are forward biased, and in this active region the emitter base junction is always forward biased and the collector base junction is always reverse biased. Now, this is the output characteristics. What is output characteristics? Output characteristics is the graph of IC versus VCE keeping the base current IB constant. Now, we have marked all the three regions of operation: cutoff region, below the IB equal to 0, below IB equal to 0 we may get current equal to 0, IC collector current equal to 0, but we have shown some current that is due to leakage currents. This region is due to leakage currents. What is that leakage current? ICBO. Let us not worry about ICBO. Now, we are concentrated on DC load line. DC load line. So, the DC, let us consider the following circuit to draw the DC load line. So, here is a circuit, figure 1, DC load line. To draw the DC load line, we are taking the help of figure 1. Figure 1 consists of transistor Q1 and then RC and then RB. This circuit is called as fixed bias circuit. We will be discussing in detail what is fixed biasing later in the next session maybe, right. So, in this circuit IC is the output current, VC is the output voltage. So, the proper maintenance of IC and VCE is called as biasing, BJT biasing, right. So, before drawing the DC load line, we need to touch up upon this circuit. So, this circuit consists of RB, RC and Q1, VC is there in the output side and IC is there at the output side, right. But we have missed one thing here. So, this region is called as VCC. I have missed one plus VCC here. This is a plus VCC. So, the supply for the device circuit, right. Now, how to draw the load line? To draw the load line, we must apply Kirchhoff's voltage law to the output loop. What is the output loop here? The output loop here is it starts from this plus VCC and then negative minus VCC is connected to the ground. So, this is the region. So, actually there will be positive terminal here, negative terminal here, negative is connected to the ground, positive is connected to this point. So, this loop is called as the output loop, CE loop or the output loop of a BJT. Now, applying KVL to this output loop, we get what we get, minus to plus we will consider it as positive. So, here VCC is there, VCC minus to plus is there. So, when we move from minus to plus, let us take it as positive. So, plus VCC and then what is Kirchhoff's voltage law? The algebraic sum of voltages in a loop is equal to 0. So, VCC already voltage is there. Then when we come to RC and IC, when we multiply IC and RC, it is a voltage drop in the RC. Then plus VCC minus IC RC minus VCE equal to 0, that is equation 1. So, when we have to consider two cases here. Case 1, I want to get the point on the one point on the x axis, that is IC axis, one point on the IC axis and one point on the IC axis, one point on VCE axis and one point on IC axis. To get one point on VCE axis, we must put IC equal to 0. So, when we put IC equal to 0 in equation 1, we get point A, which is VC is equal to VCC, VC is equal to VCC. Now, let us consider this as point A. So, VCE is equal to VCC. At this point, VC is equal to VCC. Next, case 2, I want to get point on the IC axis. I want to get point on the IC axis. Therefore, I will put VC equal to 0. VC equal to 0. Put VC equal to 0. Put VC equal to 0 in equation 1. We get VCC minus ICRC equal to 0. Therefore, I will get IC is equal to that is here IC is equal to VCC by RC, VCC by RC. So, that point I will call it as point B, wherein IC is equal to VCC by RC, VCC by RC. So, first we need to okay. So, once we fix the points on VCE axis and IC axis, we need to join them to get a DC load line. So, now here when we come to this point, so this is the thing. Now, the points A and B are marked on IC and VCE axis of the output characteristics of BJT. The line joining of points A and B on the characteristics is called as DC load line. Let us join these two lines. So, Let us join these two lines, and this line is called as a DC load line. DC load line. Why it is called as DC load line? Why it is called as DC load line? Let us this line is called as DC load line when we take the slope of this line, the slope of this line. When we the line joining, I'll say this. This is the line called, this line is called as DC load line because the reciprocal of slope of this line gives us directly the load resistance RC. How do we do that? I will take here. What is the slope actually? Slope is given by y by x. We know that, right? Slope y here is, it is this point from 0 to this point. At the point IC is given by VCC by RC. So, y here is VCC by RC divided by what is the x? X is VCC. Therefore, I will write VCC. So, VCC goes and slope is equal to, slope becomes 1 by RC. If we take the reciprocal of slope, we get RC. RC is what? It is a collector resistance. It is a collector resistance. It is a collector resistance. Collector resistance means when we are not using a external load resistor, then automatically by default the RC, collector resistance, becomes a load resistance. Collector resistance becomes a load resistance. Therefore, when we take the reciprocal of slope of this line, we get the load directly. Therefore, it is called as load line. And under DC conditions, we have drawn this load line. Therefore, it is a DC load line. So, this is how we draw the DC load line. Now, what is the use of this DC load line? It is fixing the operating point, or the fixing the bias point, or fixing the Q point of the device. The line joining of output characteristics of BJT and the DC load line are called as the operating points, or the bias points, or the Q points. Let us say in this diagram, the line joining of the output characteristics with the DC load line, one point is here, I will mark like this, and the other point is at this point, next point is at this point, next is this point, next is this point. So, all these are operating points of the BJT. So, the operating point or the bias point or the Q points of the BJT are these points. Let me mark this as A, B, C, D and then E. Now, A, B, C, D, E are the operating points of the BJT. For getting faithful amplification, we need to choose the operating point exactly to lie at the center of the active region. When we consider A, B, C, D, E points, approximately point D acts as a lies at the center of the active region. Therefore, we can choose this as Q point or the bias point. So, for getting faithful amplification, we must fix the operating point or the bias point or the Q point at the center of the active region. Otherwise, we get the unfaithful amplification. So, from bias point, what we get from the bias point? So, when we fix this bias point or the operating point, when we extend this downwards, to touch the IC axis, we get one point called as ICQ, one point called as VCEQ, voltage VCEQ. I will mark this with this circle. Then when we extend this Q point horizontally to touch the Y axis, at this point we get the current called as ICQ. So, what are these ICQ and VCEQ? ICQ is the quiescent collector current and VCEQ is quiescent collector to emitter voltage. These two values should be maintained during the passage of the weak signal in the amplifier, then only we get the faithful amplification. So, once we get the Q point, we will come to know that what is the amount of base current which is to be applied at the input of the BJT. So, the which base current we have to apply? It is IB3. When we apply IB3 to the base or the input circuit, when we go back to the previous slides, the circuit which we considered is this one. So, this is the circuit we have considered. At the input, I have written here IB. So, which IB we must apply here? It is IB3 we have to apply. When we apply IB3 at the input side, when we apply IB3 at the input side, at the output circuit we get ICQ and VCEQ. These two collector current and collector to emitter voltage must be maintained during the passage of the weak signal which is to be amplified. Now, going to bias point. So, here the Q point is D here. D here is a Q point which gives us VCEQ and ICQ, quiescent voltages and currents. Then IB3, we will come to know this point corresponds to the base current IB3. When we apply this base current IB3 at the input of the circuit, we get VCEQ and ICEQ. And these two values represent the point called as bias point or operating point or Q point. It is usually represented by an ordered pair. It is usually represented by an ordered pair which is as shown below. So, Q is ICQ, VCEQ. So, this is the operating point. This is the Q point or operating point, or it is also called as bias point, right. So, when in order to get faithful amplification, we need to operate the transistor at this point, point D, for the above circuit. Next. So, here I have given the bias point, we get from the bias point we get the base current IB, and when we apply this value of base current, we get the proper IC and VCE values which gives us faithful amplification. These values of proper voltage and current can be represented as an ordered pair given by Q is equal to IC and VCE. There I have written ICQ and VCEQ. We can also write like this. Then, so on the characteristics which I have written on the board, same thing I have written on the PPTs. So, this is the operating point. So, this is the operating point which gives us VCE and IC, and IB equal to capital IB we must maintain at the input side of the circuit. Next, let us take one problem on operating point. For the transistor circuit shown in figure 4 below, determine the operating point Q and estimate the maximum symmetrical output voltage swing. Note that VCC is equal to 18 volts, RC is equal to 2.2 kilo ohms and IB is equal to 40 microamps. So, again the same circuit is used here. Here the fixed bias circuit, figure 4 represents fixed bias circuit. For this again we need to apply Kirchhoff's voltage law to the output, and we get VCC minus IC RC minus VCE equal to 0. And then from that VCE is equal to VCC minus IC RC we get. We need to fix the point A. So, how do we fix the point A? That is VCE. VCE equal to VCC when we apply IC equal to 0. Therefore, VCE is equal to VCC is equal to which is 18 volts in this problem, Next, In the same equation, when I apply Vc equal to 0, then 0 is equal to Vcc minus IcRc, which gives us which implies Ic is equal to Vcc by Rc, which is equal to 18 volts by 2.2 kilo ohms. If you calculate this value comes out to be Ic is equal to 8.2 milliamps. So, point B corresponds to 8.2 milliamps. So, in this problem, so point B is at 8.2 milliamps, which I am marking on the board, and then VCE will become 18 volts. This is VCE, which is equal to VCC, which will be 18 volts, and the line joining of these 2 points gives us again the DC load line, and therefore operating point from this DC load line which we get is IC is equal to 8.2 volts milliamps, AC is equal to 8.2 milliamps, and VC is equal to 18 volts, and the maximum symmetrical output voltage swing. So, what is this maximum symmetrical output voltage swing? So, when we take the output V out, it is, I told you, positive half should be same as the negative half, and this is the amplified output voltage. The 18 volts is splitted into this whole voltage is called as 18 volts, and out of this 18 volts, positive half will be plus 9 volts and negative half will be minus 9 volts. Therefore, the symmetrical maximum symmetrical voltage will be plus or minus 9 volts. Here I have marked here plus or minus 9 volts. The VCE versus IC graph, DC load line and the Q point for this problem are shown in the figure below. And some more. So, the diagram shows the entire IC versus VCE characteristics, DC load line and the Q point. This diagram has been taken from David A. Bell. Right. Now, let us discuss the BJT biasing techniques. There are 3 types of BJT biasing techniques. They are base bias technique, fixed bias technique, it is also called as fixed bias technique, then collector to base bias technique, and then last one is voltage divider bias technique. So, out of these 3 techniques, collector to base bias technique is out of our scope of the syllabus. Let us not discuss that. So, we will be discussing base bias or fixed bias technique, and the last one, the voltage divider bias technique. So, in this session the base bias or fixed bias technique. What is base bias or fixed bias technique? We will be using one fixed large value of fixed resistor between, which I am marking on this PPT. This is RB which is fixed between VCC and the base of the BJT, When we fix this value RB, which takes care of the BJT operation in the active region, wherein emitter base junction is forward biased, collector base junction is reverse biased. This is been taken care by this one fixed resistor, therefore, it is called as fixed bias technique or the base bias technique. Now, again here we need to fix the operating point, we need to draw to fix the operating point we need to draw the DC load line. DC load line must be drawn and the operating point must be fixed, and then we need to note down ICQ and VCQ. To do that, we will be taking the help of KVL and KCL equations. Next. So, what is the summary of this session? We will be discussing biasing techniques in the next session. So, the summary of this session, we started with prerequisites of BJT biasing. What are the prerequisites? What is biasing? We discussed what is biasing, the importance of DC load line, the importance of DC load line. The DC load line is used to fix the operating point of the BJT. To fix the operating point of the BJT at the center of the active region, to get faithful amplification, we take the help of DC load line, and this DC load line is called as DC load line because under DC conditions we draw this load line, and this is called as load line because the reciprocal of slope of this line gives us directly the load resistance, which is RC. And we studied what is bias point, the operating point. Let us define operating point or the bias point. It is a point on the output characteristics of the BJT to be fixed at the center of the active region to decide what amount of base current we need to apply at the input of the BJT circuit to get faithful amplification, to get properly biased. We need to get the proper maintenance of IC and proper maintenance of VCE during the passage of the weak signal, and that can be achieved with the help of bias point or the operating point or the Q point. And we have also taken one problem on bias point, and we fixed the operating point again, and we noted down ICQ and VCEQ, and then from this ICQ and VCEQ we represented the Q point as an ordered pair of ICQ and VCEQ, and then we noted down the base current, and that base current is applied at the input side of the BJT circuit to get the faithful amplification. And types of biasing techniques, there are three types of biasing techniques. First one is fixed bias or the base bias, and next one is collector to base bias, last one is voltage divider bias. In these three techniques, only two techniques is restricted in our syllabus, and collector to base bias is out of syllabus. So, we will be discussing, we just touched upon fixed bias technique, we just saw the circuit diagram this class. Next session we will be continuing with the biasing techniques, and this is the summary of the session. Thank you.